Hi, my name is Jim Harris. I'm a principal software engineer in Intel's Data Platforms Group and one of the SPDK core maintainers. Nate, thanks for that introduction. As Nate said, I'm going to give a little bit of a talk on SPDK and the State of the Union. So today, going to cover three main topics. So the first one's going to be state of the community. I'm going to talk a little bit about some of the community participation, some of the major milestones that we've hit over the last year. Next, going into state of the technology. So talking through some of the key features that we've added over the last 12 months. There's, of course, a ton of work that's been done. We're only going to hit the highlights, but want to give you some of those highlights here today. Next, we're going to go over state of the future. So talking about what are some of the current focus areas that the project is working on and ones that are going to come up probably over the next 12 to 18 months. Okay, so first, state of the community. Nate already touched on this SPDK symbol. I will say, just like Ben Walker got his PhD in web design, Nate also got his PhD in graphic arts. He put this symbol together. For those that haven't noticed, you see this little S highlighted here, and it's supposed to emulate a racetrack. So it's really kind of showing SPDK and the performances you can get from its libraries and from its programming model. So first, if you're like me, COVID has not been fun. It has impacted the project. We have regularly had face-to-face meetings over the last few years, and over the last 12 months, it was the first time in 5 years that we didn't have any face-to-face summits, the first time in 4 years that we didn't have any developer meetups. Those have both been huge. It's been great to be able to get people together, people who've been working on SPDK, who have questions. Really hope that this forum today is going to be really useful. I'm glad we're going to have some Q&A to go through stuff, but we do realize that it's not quite the same as when we can all get together and have discussions, and we hope that we'll be able to do that soon. But the project still moved on. We still had our 4 quarterly releases over the last year, including our second LTS release, which was released in January, the 21.01 release. And we have had 2 virtual summits over the last year. So we had one here in the US last June. Our team in China also had one back in November. And so in lieu of being able to do face-to-face, at least we're being able to have some of these virtual summits to talk about what's going on in the project. And next, we really want SPDK to be an inclusive community. If you've been following the tech industry, there's been a lot of talk about using inclusive naming in our engineering terminology, and the project has made efforts on that regard, and we've adopted guidelines, made a number of changes to use more inclusive naming in the SPDK project. Okay, so looking at some of the metrics, some of the statistics. So we kind of like to show the patch commits over on a yearly basis. And so each of these rows here roughly is 1 year in time. The highlighted one shows time since between the April release in 2020 and the April release this year. And you can see the number of patches been very similar to what we've had in years past. We did had an uptick last year, which was good. We're kind of back to that 3,000 patches per year level. Still seeing almost 100 committers every year from a ton of different companies. I don't have like a number for you, but it's on the order of 20 to 25 different companies that are committing code to SPDK. And like any project, you have those committers who are very prolific, but we like to kind of look at, where are the patches all coming from? And we're still seeing about 35% of the patches coming, outside of those top 10 committers of the project. And that's really good. It's something that we want to encourage more of. You can see that this has really trended upwards over time as far as getting more, not just more people into the project, but more people into the project who are contributing heavily. And then we also like to look at who's going out and hitting the GitHub website. And so, you can see we're continuing to trend upwards on this. When you look at the number of unique visitors we have to the SPDK GitHub project on a daily basis, we're up about 18% year over year and about 5% year over year on the number of page views. Okay, now let's talk a little bit about the technology. So as I mentioned earlier, I'm going to go through some of the highlights that we have in the project over the last year. Of course, one of the biggest ones that we always focus on is performance. I'm not actually going to touch on performance today, primarily because, as Nate mentioned, we're going to have a whole talk on it from John Kariuki and Karl Latetsky. And so I'm going to let them cover the performance and what's going on with the project there. So one of the big ones is the SPDK scheduler framework. We've talked about this in the past. You probably heard me actually talk about it in the last State of the Union as something we're going to be working on, and we can say now that we have something delivered for this. We added this in the January release to 21.01 release. And so what we have now is we have pluggable scheduler modules. And what this lets us do is when we have these pulled mode applications, you know, they're pulled mode, and so you have a lot of cores that are running, but then you have cases where there's not a lot of work being done, right? The application may be mostly idle, and you want to be able to shut cores down, be able to save some of that power. And so what these scheduler modules allow you to do is to be able to analyze the thread and the reactor metrics and then be able to make decisions on it and being able to move these SPDK threads between reactors. So a little bit on the nomenclature here. When we talk about SPDK threads, those are not POSIX threads. They aren't heavyweight threads. Those are lightweight threads that are an SPDK construct. And we only have one real POSIX thread running in each core, and that's the reactor. And so what it means is when we move threads between reactors, it gives us the ability to shut a reactor down, which means that we can shut a core down. And that's really one of the primary driving factors to implementing this framework. And it's not just shutting the cores down. We've also added the ability to add an optional governor, which allows you to govern the CPU frequency. So for example, on like Xeon platforms, we have the speed select technology. And so we utilize the DPDK RTE power library so that the scheduler can also ramp the frequencies for cores up and down based on the current workload. We've also added some experimental interrupt, or what we call blocking mode. This is not something that we are intending to implement throughout the entire SPDK library set, but we do have limited support in the vhost block library and the NBD front end if you're using the AIO backend. So it actually allows you to be able to use a fraction of a core, still be able to use the SPDK user space code base. As of course, it's not going to be as highly performing, but for those use cases where something like that can be useful, we do have some support for that. Okay, so next, zone namespaces. Zone namespaces was added to the NVMe. It was ratified in NVMe last June, TP 4053. Matthias Bjorling from Western Digital was the lead author on that. For those that aren't familiar, zone namespaces, it allows the host to be able to kind of collaborate with the SSD on doing data placement. So you have some aspects of or all aspects of the flash translation layer that move up into the host. And there's a couple reasons you want to do that. The primary one is that there's a lot of applications, a lot of workloads where the host understands how the data should be placed, what the lifetime of that data is, much better than what the SSD, the SSD knows about it. And so it allows you to reduce the write amplification, allows you to reduce the media over provisioning, so you can get better performance and make better use of that NAND media. So there's been quite a bit of SPDK enabling that's happened over the last year. A lot of this was led by Western Digital, Nicholas Cassell, with support from Samsung. Simon Lund did a lot of the initial FIO work. And the support had to go in a few different layers. So first at the core NVMe driver, giving it the ability to just be able to recognize different NVMe command sets, such as the zone namespace command set, and support for some of the other identify and log pages and stuff that are needed there. There was also support added to the BDEV NVMe module. So a while back, we actually added a zones abstraction at the generic BDEV layer. Originally, it was used, we emulated zones with open channel SSDs. We also added some kind of test modules to take like a basic SSD and be able to sort of emulate zones just for testing purposes. But the changes that Nicholas made in the BDEV NVMe module allowed us to also now report up an NVMe zone namespace as a first-class zone BDEV. And then finally, of course, like FIO, SPDK has made a concerted effort to have a FIO plugins that support the latest and greatest workloads. And so the work here was both to the NVMe and also the BDEV FIO plugins to be able to support zone workloads. Okay, CSI, so for Kubernetes container storage interface, we had a plugin that was added last July, currently in beta status. This is actually not part of the primary SPDK repository. We have a separate repository called SPDK CSI for that. And ARM Yibo Kai has been developing, did a lot of the initial work on this, is continuing to maintain that. And what it enables, and you're actually going to see this later when Monica Kanguva does her demo later today, is to do logical volume provisioning with SPDK, and then be able to give pod access to those logical volumes either over iSCSI or NVMe over Fabrics. And so definitely tune in for that demo to see more details on how this works. Okay, vfio-user. So this is another one. You're going to hear a talk from Ben Walker from Intel and Thanos Makados from Nutanix later on. They're going to go into a lot more detail than what I'm going to show here. But really, vfio-user itself is not an SPDK thing. It's a framework for implementing PCI devices in user space. Nutanix has been driving this. They have a GitHub repository out there where you can get this library. And so this is not NVMe specific or SPDK specific. It's just for implementing PCI devices in user space. But a lot of this came out of wanting to be able to serve storage to QEMU VMs using the NVMe interface with an SPDK application. So in the past, you would use something like VirtIO in like our vhost block or vhost SCSI target to do that. But as the industry moves more and more towards NVMe, wanted to have that as an option too. We had looked early on at some options, maybe trying to use VirtIO and vhost with NVMe. Didn't really fit really well, and that's kind of how this came about. Just at a high level, basically we've taken the NVMF target and now using it for not just fabrics, but for things like vfio-user. And Ben's going to talk quite a bit more about this. The upstream support's still a work in progress. And like I said, there's a lot of similarities to vhost as far as kind of how the overall architecture works, but there's some of the specifics that are quite a bit different. And the other thing we've done here is we've actually added it as a transport on the initiator, the NVMe driver side as well. So it's not limited to only being able to consume NVMe storage from a QEMU VM. You can have another SPDK application running on the host that can also communicate with the SPDK target that's serving up vfio-user storage, be able to connect to it that way as well. Okay, let's a little bit on state of the future. So where is the project going? What are we working on now, and where is it going to be moving? So one of the big ones, one of the big buzz phrases today is cloud native. Everything's about cloud native, and you're going to hear Paul Luce and Ben Walker talk about this quite a bit more in their upcoming talk. So I'm not going to go into a ton of detail here, but some of the big things that we're looking at with SPDK is like, how do we run SPDK without having any hardware assumptions, right? There's some things that SPDK needs, but we want to be able to deploy SPDK more broadly. And so how do we alleviate some of those hardware assumptions? How do we be able to make sure SPDK can run in a broader set of environments? And you'll see Ben and Paul are going to talk about some of the things SPDK is already doing right today. I think there's some good decisions we've made in the past, which are going to make this a lot easier, but there still is quite a bit of work to do. And I'm not going to go into a lot of details, not going to do a lot of spoilers. Please attend the upcoming talk, and they're going to go into a lot more detail on that. Okay, next. IPU enabling. So IPU, Infrastructure Processing Unit. This is a term that you may have just started hearing recently based on some talks that some of the Intel executives have given, and some of the alternate names you've probably heard of are like smart NICs with like storage offload or DPUs. And so that's basically what an IPU is. And so I think SPDK really plays a key role in this IPU ecosystem. And so there's a lot of work SPDK has already done, and there's going to be more work down the road to help SPDK kind of fit into IPUs in this data center of the future. So a few things that we are working on, are going to continue to be working on. One is better SPDK thread schedulers. So we have the framework in place. We want to have some really innovative schedulers to be able to make best use of those CPU cores that are running on those IPUs that are running the SPDK application. Support for more host interfaces. So we talked a little bit about how the NVMF target has a generic layer that we can plug multiple transports on top of. That suits very well to IPUs. But VirtIO is not going away. There are devices out there today that can present VirtIO interfaces to the host from a piece of hardware. And so, we think SPDK probably needs to do some more work in this area to have similar pluggable transport support like NVMe does. And the next three, I'm going to go into some more detail and some specific slides, but first is telemetry. More understanding of what's happening inside of an SPDK application. NVMe Multipath, so cases where you have a host that's communicating with an IPU, but then within the IPU it can access storage over multiple interfaces, and then also computational storage. Let's talk a little bit about telemetry. So there's a lot of things for telemetry that you can do today, just like you can do with any application, right? You can you can use common profiling tools, you can use perf top, you can use top, you can use a lot of those things. But when you look at SPDK applications, there's a lot going on inside, right? We talked about the threading model. The threading model is very different, right? We have reactors, which are just a thread. But how do you get information on these SPDK threads that are running inside of the application? How do you get information about the pollers and the timers that are running inside of each of those SPDK threads? And then also, how do you get more information about the IO processing, right? Like, it's a very high performant storage application. How do you get more information about what's actually happening, like detailed steps of IOs as they're going through the pipeline? So one of them is SPDK top. So you're going to see Maciek Szwed. He's going to give a demo on SPDK top later today. And so this gives you the ability to really look at in real time what's happening inside of your SPDK application. Which threads are running on which reactors? What are the pollers doing? How much of the time are how many times are they executing? How many times are they reporting that they did work versus they checked for work and there was no work to do? So it can be really, really useful. And, we're doing a lot more development on that and getting a lot of feedback from it as well. We're getting a lot of bug reports, which you don't like bug reports, but bug reports are good because it means people are using it. And so I think this is a really cool application that's going to get a lot more adoption by the SPDK community. So looking at things like, user space, like instrumenting SPDK with USDT probes, user space dtrace probes. So being able to inject code points where you can see specific things that are happening inside of the code. So for example, within SPDK, you have some fairly complicated process when you have like in the NVMe target, when you have queue pairs being constructed, right? So a queue pair comes in on one thread, and the queue pair is actually going to get pulled on a different thread, and so there's some back and forth that happens, and we've had some bugs in this area, and so can we put dtrace probes in to help make that a little bit easier to debug in real time, and then also just making it easier to use like BPF trace or BCC to be able to in real time run probes against an SPDK application and get information about what's happening. And then also extending the SPDK trace capabilities. So being able to, we have tracing already in SPDK where you can actually, it's a custom implementation for SPDK where we can capture for an IO, like different steps through the IO pipeline and get like literally like nanosecond granularity on how that goes through. And it's been really useful, but one of the things it doesn't give you an idea on is it just tells you there's an IO, and maybe that it was on some queue pair, but you don't have any information about the queue pair. You don't have any information really about which BDEV it went to. And so Konrad Steiber has been doing a lot of work at looking at how do we combine data that we can get from like a user space dtrace probe script with the SPDK trace capability to merge this information together, right? So now you can be capturing very high frequency trace point data from an SPDK application, and then also be able to marry that with data from probe points where when queue pairs were created and when they were destroyed, and for example which NVMe subsystem they're being sent to. And so it really it pulls those two things together to extend and give a lot more telemetry information. So next, NVMe Multipath. So there's been quite a bit of work that's happened already on the target side for this. Shuhei Matsumoto from Hitachi, one of the SPDK core maintainers, has been doing a lot of this work as far as being able to report, ANA, asynchronous namespace associations. I'm sorry, asymmetric. And now we're looking at, what do we need to do on the initiator side? And so, on the initiator side, NVMe Multipath, it's being able to support multiple routes or paths between the application and the NVMe namespace. And of course, this is going to be useful on IPUs where you want to be able to have one IPU be able to access its storage across multiple paths. And so this is fairly complicated. There's a fairly extensive patch set that's out that's under review right now. It uses all the asymmetric namespace access to be able to drive this to identify the optimal path. This is something that's going to be a significant focus, at least over the rest of this year, to get this implemented. Okay, next, computational storage. So I'm going to talk about computational storage more broadly today. There is an NVMe technical proposal that's in definition phase. It hasn't been ratified yet, so there's still a lot of TBD work that's going to happen there. So I can't go into a lot of details on where that's at, but computational storage itself is, there's a lot of talk about this in the industry. SNIA has a work group that's been focusing on a lot on this, defining like what are the usage models, what's some of the terminology, what are some of the big use cases. And so SPDK fits really well into these types of use cases. And so when we kind of look at how this works, typically you've got some on-controller compute engines that need to process some data. So it could be an FPGA or an ASIC that maybe has some, compression or decrypt offload. It could be CPU cores that maybe can run some downloadable programs. And then the idea is that the host can orchestrate moving data between the host, between the media, like the SSDs, and then some local memory buffers that are inside of the NVMe controller. So instead of, today, you pull data from the SSD up to the host, and then the host does all the processing. Now you can have more of this functionality down in the NVMe controller itself, be able to keep some of the data movement inside of the IPU and be able to send the result back up to the host. And so kind of, when we look at the basic data flow here, a really common one that is really key is, being able to do data analytics. And so, doing things like reading blocks of data into this local memory buffer, being able to decrypt and decompress it using offload engines that are inside of the NVMe controller, being able to filter it, maybe with some sort of fixed function offload, maybe with a downloadable program, something like an eBPF program that the controller can execute to be able to iterate through that data and identify matches for something. And then finally, being able to transfer that result back up to the host, and so then at that point, you're transferring a much smaller amount of data. And so you are saving that host, PCIe bus bandwidth, or saving memory bandwidth up on the host. And so, we think that this is going to be a pretty key use case over the next few years, and something that SPDK is going to play a prominent role in. Okay, so the last one I'm going to touch on today is something called Right Shaping RAID, WSR. And so the Optane software team here at Intel has been working on this, and we're really excited to see some of these things move into the SPDK upstream over the next year or so. Yeah, before I get into the details there, so a lot of this is based on the concept of having one of these FTLs, a flash translation layer, running in the SPDK application. So, the application is doing reads and writes, it's coming into this FTL, and then this FTL is basically going to use three main components as part of this right shaping RAID solution. And so the first one is having kind of a persistent write cache, where the writes are coming in, they're getting staged in a very high performance SSD, something like an Intel Optane SSD. So it has very high throughput, very, very low latency. It allows us to aggregate writes to an optimal write size, meaning at some point this data is going to need to go to some sort of, cost optimized high capacity NAND, but you want to be able to aggregate them so that you're writing very large chunks at a time to take best advantage of that NAND media. And so, of course, this also gives you power fail safety, right? Because we're writing it to an SSD. It's not just in volatile DRAM. It allows us to do early write acknowledgement, right? So now we can get better performance on those writes because we can immediately acknowledge them once they've hit the SSD. Of course, when we do this, now there's a level of indirection here, right? Because we have writes coming in and they're all getting staged into an SSD, meaning that the logical block addresses that the applications, sends down aren't going to match the logical block addresses where the data actually ends up on the backing NAND. So we need to have this logical to physical map and the extra metadata for that. And so that's going to be another big component here. And this is where having like persistent byte addressable memory like Optane PMEM is going to be really useful for that component. And then finally here we talk about write shaping RAID. This says RAID 5. There's nothing here to say that it has to go to like some sort of rated volume. We think that long term that's probably going to work really nice, but it doesn't have to be rated. I think the key part is that it needs to be a cost optimized NAND tier. Something like ZNS, something where you have, like QLC drives and maybe have like a very large indirection unit. It's not maybe 4K, but maybe something like 64K. And so you can do writes. You want to do very, very large writes to it though, to make take best advantage of the media. But with this architecture, the RAID 5 implementation can be really simple. You can do full stripe writes, right? So we don't need to do any read modify writes. We basically aggregate everything in the Optane SSD till we get a full stripe, and then we can write that whole stripe all at once. And so this gets rid of the typical penalties you get with RAID 5. You're not doing in-place updates. You don't have to do those read modify writes. You're avoiding the RAID 5 write hole. That makes for a really nice solution. So this is something else to kind of keep an eye out over the next year. So hopefully you have a better picture of what's going on in the project. Really appreciate you tuning in today. We're gonna have some time for some Q&A, so please stick around for that. Hope you enjoy the rest of the talks, not just today on SPDK, but the next couple of days, PMDK and the Intel Performance Analyzers. You're gonna see a lot of really good presenters present a lot of really good material, so please take advantage of that. We'll have our Q&A today, but of course, if you have more questions or looking to contribute, looking to download stuff and kick the tires and use it, join the community. So you can go out to our website, spdk.io/community. You can get links to our Slack channels, to the mailing list, to timelines for our community meetings. So we have meetings twice a week, friendly to all time zones. So please take advantage of that. And finally, here's a picture of Hayes Mansion, where we've had the summits in years past. Hopefully next time we do this, we'll be able to do this in person. It's somewhere like the Hayes Mansion. Thank you very much.